Okay, we will see now m-derived filters. So we have discussed about constant K filters, but there are certain disadvantages due to which we have to go for certain other type of filters which are known as m-derived filters. And we will see why we need to go for m-derived and how they are going to be designed. So first of all, there are two disadvantages of constant K filters. They are like the attenuation is not sharp in the stop band and the characteristic impedance varies widely in the pass band. So to avoid this, if you have observed the characteristics from the constant K filters, the attenuation was not sharp. That means it is slowly changing while the frequency is changing, but it is not required at some time, or for some applications it might be required that we need attenuation change at a sharp manner, in a short manner. Okay, that means we are not getting the ideal filter nature. That's why to avoid that we need to go for m-derived filters. So that's why if the constant K filter has to be regarded as a prototype filter, it is possible to design a filter to have rapid attenuation in the stop band and the same characteristic impedance as the prototype throughout the pass band as well as stop band. And such a filter is called as m-derived filter. Right, now we will see how we can design. First, before discussing m-derived low pass and high pass filters, we will see the T section and pi section types of filters in a generalized manner. Then accordingly we can design them to act as either low pass filter or high pass filter. Okay, so here the constant K and m-derived T sections are shown in the figure 15.27. This is for T network or T section. So if you observe, the constant K T network is identical to that of m-derived T network, except that the series arm is multiplied by the multiplying factor of m. Fine, so that can be seen here. Here in the constant K filter, if the impedances are Z1 by 2, Z1 by 2 in case of series arm, the m-derived filter will be having Z1 by 2 into m, which is also same here because they are symmetrical T networks. Fine, and there is no change in the shunt impedance or shunt arm resistance or impedance, that is Z2. Z2 is same. Okay, now we have already derived the constant K T section characteristic impedance, that is Z0 T, which is nothing but square root of Z1 square by 4 plus Z1 Z2, and now this Z1 is going to become mZ1 if it is a m-derived filter, right? Then you just substitute or replace Z1 with mZ1, then we will get m-derived filter characteristic equation. Sorry, it is given in a wrong manner here. Here the shunt impedance is also changing, right? So it should be Z2 prime here. So it is not clearly mentioned in the textbook. So now we are changing both series arm resist impedance as well as shunt arm impedance to get m-derived filters. That's why we have replaced Z2 with Z2 prime in the characteristic impedance equation that can be seen here. Okay, right? So Z2 is replaced with Z2 prime, and in place of Z1 we got mZ1, right? So when you equate the characteristic impedance of these two networks, that is constant K and m-derived filter, what we will get? We will get the condition for Z2 prime, or how to choose Z2 prime. Fine, so that is also having the multiplying factor m inside of it in its equation. So accordingly we have to choose Z2 prime. So for that particular purpose, what we are doing, the characteristic impedance of the networks are made equal to each other. Okay, so when you solve this, you will get this, you can practice it. That means the shunt impedance should have two different impedances which are connected in series, and their values are 1 minus m square by 4m into Z1 and Z2 by m, and this Z1 Z2 are coming from the constant K filter, right? So for converting constant K filter to m-derived filters, the series impedance should be changed to m into Z1 by 2, whereas shunt impedance has to be changed to the series combination of these two impedances. Okay, so now in order to get the or design the feasible values of impedances, the m value should be varied between 0 and 1 only, because if it becomes more than 1, what happens? We will get the negative term here. When it becomes negative, we cannot physically get the impedance, right? Fine. So that is how we are going to change, right? So in a same manner, we can derive the equation for m-derived pi section, right? We will see in a similar manner it will be, but if you observe here, in case of pi section, the Z1, that is series arm resistance, is chosen as Z1 prime, whereas shunt arm impedances or resistances are chosen with factor of 1 by m, whereas there in case of T filter it is factor of m, and here it is factor of 1 by m. That is an important difference here, right? So now we also have the constant K pi section characteristic impedance, that is given with this relation, and when you substitute Z1 as Z1 prime and Z2 as Z2 by m, what you will get? You will get this one, and when you equate these two, you will get a relationship between Z1 prime with respect to Z1 and Z2. Okay. So when we further simplify this, we can represent it like, in the end, mz1 into 4m by 1 minus m square into z2 divided by mz1 plus 4m by 1 minus m square into z2. So with this we can say that this is a parallel combination of different impedances, and they are nothing but mz1 and 4m by 1 minus m square into z2, whereas the shunt impedances are 2z2 by m, 2z2 by m, and the series arm impedance is the combination of two different impedances, and their values are mz1 and 4m by 1 minus m square into z2. So this is the difference between m-derived T filter as well as pi filter, or T section or pi section. Now based upon these we can get low pass and high pass filters, that we will discuss in the next lecture. That's it. Thank you.